In this section, we are going to talk about using synthetic division to factor polynomials. And this is a technique that we use to quickly find the zeros, and then of course get the factors based on those zeros. So we're going to talk about synthetic division, we'll talk about the remainder theorem and the factor theorem, which are intimately connected to synthetic division. So let's start by just talking about polynomial division. We want to find the zeros of this function here, this polynomial, given that x equals 2 is a 0. Now, if x equals 2 is a 0, that actually tells us that x minus 2 is a factor. Okay, so this function, f of x, can be written as x minus 2 times something. Now, what that thing is, we're not sure. What I'm going to do is I'm going to write this. I've got x cubed plus 4x squared minus 5x minus 14 equals x minus 2 times something else. I'm just going to call that something p of x. Okay? We know that x equals 2 is a 0, so x minus 2 has to be a factor. Now, in order to find the rest of the factored portion, we can divide both sides of this by x minus 2. So x cubed plus 4x squared minus 5x minus 14 over x minus 2 is equal to p of x. So we need to figure out what this thing here is. Now, in order to do this division, we can do long division and we can do synthetic division. Now, long division is what we're going to do here because we haven't quite talked about synthetic division yet. So let's go ahead and do long division here. Okay, as a reminder, you take your polynomial that you're dividing, okay, and you put it underneath your division. And out here, we do our x minus 2. Okay. Now, for long division, what we do is we take x cubed, the first term here, and divide by the first term here. So x cubed divided by x is x squared. Okay. And then we take this x squared and we multiply it by this divisor. So x squared times x is x cubed, and x squared times negative 2 is negative 2x squared. We then subtract this from the polynomial that we started with. So the x cubed will cancel, okay, and the first term should always cancel. And then we have here 4x squared minus a negative, so plus 2x squared, and that is 6x squared. And then we've got the minus 5x, there's nothing to subtract from that, so we just carry it down. And the same thing with the minus 14. Okay, now we have the same process that we do, okay? We take this first term, 6x squared, and divide it by the first term here. So 6x squared divided by x is 6x, and we put that here, plus 6x. And we multiply the 6x by the x minus 2. So we have 6x squared minus 12x. And then we subtract that. So the 6x squared cancels. We have negative 5x minus a negative, so plus 12x, and that's 7x. And then the minus 14 we carry down. And then we do it again. 7x divided by x is 7. So we have plus 7. And we multiply the 7 by the x minus 2. So 7 times x is 7x. And 7 times negative 2 is negative 14. And then we subtract this. And here, everything cancels, so we get a 0. Now, we know that we're going to get a 0 for this one because we know that x minus 2 is a factor of the polynomial, so it should divide evenly, okay? And so what we're left with, this x squared plus 6x plus 7, that's this p of x here, okay? Now I'm going to go back to this first form, which is that I had a factored form, which was an x minus 2 times p of x, and we went through this process to find that p of x. So times x squared plus 6x plus 7. Okay. Well, now I've got a quadratic, and if I want to continue factoring this, it's a lot easier now that I have a quadratic. This is x, if it's not quite easy because it's not super easy to factor. But what we can do to find the zeros, okay, is to use the quadratic formula. Okay, so we are going to do that. We have x equals negative b, so negative 6, plus or minus the square root of b squared minus 4ac, all over 2a. Okay. So we've got negative 6 plus or minus, here we've got the square root of 36 minus 28, okay, over 2. Well, that's the square root of 8, which is 2 root 2. And then we can go ahead and divide by the 2. And so we get a negative 3 plus or minus the square root of 2. And those are our other zeros for this polynomial. Okay, so we know x equals 2 is a 0. That led us to a factored form where we had a quadratic, and we could then find the zeros of that quadratic. All right, now this division that we just did is actually part of a larger picture. It's called the division algorithm, okay? And the division algorithm is just something that tells us that we can always take a polynomial and divide it by a polynomial of smaller degree, or smaller or equal degree, I should say. Okay, so here's the division algorithm. Suppose d of x and p of x are non-zero polynomials where the degree of p is greater than or equal to the degree of d. We're just setting it up here, so don't worry about all the details here, but we've got two polynomials. And what we want to do is we want to be able to divide p by d. Okay? And that's what this says. It says that there do exist these two unique polynomials, q of x and r of x. Q for quotient and r for remainder. Okay? Where we can write p of x as d of x times q of x plus r of x. And this will always be true for where r of x is either equal to 0, so your remainder is 0, or its degree is strictly less than the degree of d, which is the divisor. Okay. Now, this statement doesn't look like division is happening, but I want you to notice that if you take both sides of this equation and divide both sides by d of x, notice what happens. You have p of x over d of x equals, if I divide this by d of x, I just get q of x. And then plus r of x divided by d of x. I can just write that out as a fraction. Okay, and this looks a little bit more familiar because this is what happens with real numbers. For example, if I were to take 13 and divide it by 4, okay, I know that I can write that as a whole number. The whole number, well, 4 goes into 13 a total of 3 times, okay, for whole numbers, and then plus a remainder. Well, after 4 goes into 13 3 times, that gives us 12. We have a remainder of 1, okay, and that's the 1/4 because we were dividing by 4. So we're actually used to this just with our real number system. Now, we actually write this as what's called a mixed number, compound number, where we don't write the plus, but it's the same thing. Okay, so this division algorithm is really just telling us that we can divide polynomials as well, end up with a quotient and a remainder. Okay. Now, that is useful because the remainder connects nicely into finding the zeros of a polynomial, and it's through the remainder theorem. The remainder theorem says that if you have a polynomial of degree at least 1, and c is some real number, then when you divide the polynomial by x minus c, the remainder that you get in this division algorithm, that remainder r of x that you get, actually is equal to p of c. Okay, so the polynomial evaluated at c. So that's actually a significant result, because it actually tells us then that we can do a quick division, and if we get 0 as the remainder, that means that that what we just used was a 0 of the polynomial, which is very powerful. So we're going to jump now into synthetic division, which is a quick way to divide by something of that form, x minus c. So here we're going to divide this polynomial by the x minus 2 using synthetic division. We did this previously doing long division. All right, it was up here. It was this horrible process here. It took a lot of work. Synthetic division speeds it up for us. Anytime you're dividing by x and then plus or minus a number, you can do synthetic division. Here's how you set it up. It's going to look like this, where you've got this bracket, okay? And we list inside here the coefficients of the dividend, okay? The thing that we're actually dividing. And then whatever we're dividing by, you're going to put out here just the 0 of that thing. Okay, so x minus 2, the 0 is x equals 2, so we put a 2 out here. If it was x plus 5, then negative 5 would be the 0 of that, so we put a negative 5 out there. Okay, so you put the 0 of the divisor out here. Then we take this 1 and we just bring it down. This first number, you just bring it down and put it underneath. Then you take this number and multiply by this 0 here. So 1 times 2 is 2, and you put it right there. Then we add these numbers. 4 plus 2 is 6. And then we do it again. We take this number and multiply. So 6 times 2 is 12. And then you add. Negative 5 plus 12 is 7. And then you multiply. 7 times 2 is 14. You put that here. And then you add. Negative 14 plus 14 is 0. Okay, now the pieces here are important pieces. Okay, these right here, first numbers, those are the coefficients of the quotient of q of x. All right, this last number is the remainder. This is r of x. Now, because we're dividing by just an x expression here of degree 1, we know that our remainder will be a constant number, all right? Because our remainder always has a degree less than the divisor, okay? So that's the piece, that's what these pieces mean. So what that means then is when we do this division, okay, if I write this in an actual fraction form, that's x cubed plus 4x squared minus 5x minus 14 over x minus 2 equals the quotient. So these are my new coefficients. It's going to be 1x squared plus 6x plus 7. You'll notice the degree of this polynomial is 1 less than the degree of the dividend, and that's always going to be the case, 1 less than what you started with. Then plus the remainder over the divisor. Now, since our remainder was 0, this term actually just disappears, okay? So we can write it in this form, or you can write it in the previous form, the division algorithm form, and this is why it was written in that form, okay? Because if we write it in this form, it just gives us a factored form for our polynomial. It says x cubed plus 4x squared minus 5x minus 14 is equal to the divisor times the quotient, and then plus the remainder, but the remainder here is 0, so we don't actually need to write that. Okay, so that's the division using synthetic division. Let's go ahead and do another example. We want to divide this using synthetic division. So we set up our division by first doing our bracket. Inside here, we're going to do the coefficients of our polynomial. And you need to be extremely careful here because notice that we're missing the x term. We have an x cubed, x squared, and then there's no x term. And we need to make sure we include that when we write the coefficients out. So we have our 5x cubed, negative 2x squared, and then there's no x term, so we need to put a 0 for that. And then we have the 1. On the outside, we put the 0 of the divisor, which in this case is 3. And then we go through our synthetic division. We bring the 5 down and multiply that by 3. 5 times 3 is 15. Then we add these. Negative 2 plus 15 is 13. And then we multiply. 13 times 3 is 39. And then we add. 0 plus 39 is 39. And then we multiply. 39 times 3, which is, 117? And then we add. 1 plus 117 is 118. Now remember that these are the coefficients of our quotient. So when we divide, we end up with our quotient. 5x squared plus 13x plus 39. And then this right here is our remainder, okay? So we get plus the remainder, and then the remainder, of course, is being divided by the original divisor. So this division right here is equal to this. That's our q of x plus r of x over d of x. Let's go ahead and try this one. This one gets even a little bit crazier because we just have an x cubed and a constant. So we're missing multiple things here. So we just need to make sure that we're taking that into account when we do our division. So we do our bracket, and inside the bracket we do the coefficients. So we've got our x cubed, which is 1. The coefficient is 1. We don't have any x squared in there, so that's a 0. We don't have any x to the 1, so that's another 0. And then we have our 8. Okay. And then on the outside we put the 0 of this divisor, which is -2. We bring the 1 down and multiply. 1 times -2 is -2. 0 plus -2 is -2. And then we multiply. -2 times -2 is +4. 0 plus 4 is 4. And 4 times -2 is -8. Now 8 plus -8 is 0. So our remainder here is 0. That's nice. Okay. This division just gives us our quotient then. We get 1x squared minus 2x plus 4. We would have plus the remainder over the divisor, but that's a 0, so we don't need to worry about that. So that is the result of doing this division. Okay, let's go ahead and look at this one. Notice here, there's a couple things. First of all, the format is written as a fraction, but of course that's the same thing as just the top divided by the bottom. Okay. Second, we've got the ordering of the numerator. Okay, it's not what we expect. We're used to the highest power of x first, and then working our way down to the lowest, which is usually the constant term. So we would like to write this as -12x squared minus 8x and then plus 4. Okay. And then we are dividing that, I'm going to go ahead and write this, divided by the 2x minus 3. Okay. So this is the way we would write it normally. I'm actually going to leave it, though, in the fraction form because I want you to see something that happened, the next thing that happens, dividing by 2x minus 3. The final difference that we notice is that what we're dividing by is not just x plus or minus a number. And synthetic division only works if you have x plus or minus a number. You cannot have a coefficient in front of the x other than 1. So what we need to do is we're going to factor that number out. Okay? That number from the denominator, we just factor the 2 out, and we're left with x minus 3/2. Okay? Now I'm going to bring it to the top. Okay? And now another way of thinking about that is simply if I multiply the top and bottom by a 1/2. Then in the bottom, it just cancels out, but now the 1/2 needs to distribute along the numerator. So I end up with a -6x squared minus 4x plus 2 divided by x minus 3/2. Now we are ready to set up our synthetic division. So we have our bracket. Inside the bracket, we do the coefficients of our polynomial, -6, -4, and 2. And on the outside, we put the 0 of our divisor, which is just 3/2. We bring the -6 down, and -6 times 3/2 is a -9. And then we add -4 plus -9 is -13. Okay, now it starts to get a little ugly. -13 times a 3/2, that's -39/2. Okay, and we can add 2. 2 is equal to 4/2. So -39/2 plus 4/2 is -35/2. Okay. So for our division, those are the coefficients of our quotient. So -6x minus 13. And then this is our remainder. So we have plus -35/2 over the x minus 3/2. Now you'll notice this is ugly fractions here. Notice we can kind of go backwards from what we did at the beginning. If we just multiply top and bottom by that denominator of 2, okay, then we're going to get, in the numerator, just negative 35. And in the denominator, when you distribute the 2, you get 2x, and then minus 3. And that's the original divisor from the problem, okay, which of course is what we would expect from our division algorithm. So this here is our divided form from our division algorithm. Okay, why don't you go ahead and try this. Go ahead and pause the video and see, and this says just find the remainder of this division. Okay, see if you can try out the synthetic division, and be careful when you're setting it up, and see if you can find that remainder. Okay, let's go ahead and set it up. We've got our bracket, and inside our bracket we have the coefficients of our dividend. We've got 4x cubed. There's no x squared term, so we need to put a 0 there. Then we have a negative 5x, so negative 5, and then our 3. On the outside we put the 0 of our divisor, which is negative 3. All right, we pull the 4 down. 4 times negative 3 is negative 12. We add those. 0 plus negative 12 is negative 12. And we add multiply negative 12 times negative 3 is positive 36. And we add negative 36 plus negative 5 is 31. And then multiply by negative 3, and we get negative 93. And then we can add these, and we get negative 90. The remainder is what we're looking for, and the remainder is just that last number. So our remainder is equal to negative 90. Let me just point something out from our remainder theorem. That tells us that this polynomial at negative 3 is equal to negative 90. Let's just check it. Let's see it happen. Oops, not a negative, just 4. 4 times a negative 3 cubed minus 5 times negative 3 plus 3. Okay, that's 4 times a negative 27 for that one, right? And then we can go ahead and do our multiplication. 4 times negative 27 is negative 108. Okay, negative 5 times negative 3 is positive 15, and then plus 3. All right, and if you do this, negative 108 plus 15 is negative 93, plus 3 is negative 90. So there we see the remainder theorem in action, telling us that the remainder is simply the function value at the 0 of that divisor. Okay, let's do it here. Find p of negative 2 using the remainder theorem. This means we would like to take this and divide it by x plus 2. Okay? Divide that by x plus 2. So our coefficients of this dividend are 2, 0, negative 5, and 3. And we're out here, we're going to put a negative 2. Okay? Because we're dividing by x plus 2, since negative 2 is the 0 of x plus 2. I know that seems like kind of roundabout. All right, and we pull the 2 down, and then multiply 2 times negative 2 is negative 4. And 0 plus negative 4 is negative 4. Negative 4 times negative 2 is positive 8. Negative 5 plus 8 is 3. And 3 times negative 2 is negative 6. 3 plus negative 6 is negative 3. That's our remainder. And by our remainder theorem, p of negative 2 is equal to negative 3. And you could, of course, check that. Let's do it, actually, just so we can see it. P of negative 2, if we actually do it explicitly from our formula, we have 2 times negative 2 cubed minus 5 times negative 2 plus 3. Well, that's 2 times negative 2 cubed is negative 8. And then we do our multiplication. 2 times negative 8 is negative 16. Negative 5 times negative 2 is positive 10. And then we do it. Negative 16 plus 10 is negative 6. And negative 6 plus 3 is negative 3. So it worked out. That was our checking. All right. For number 2, use the fact that x equals 1 is a 0 of p to factor p of x and then find the real zeros of p. So, since x equals 1 is a 0 of p, I can divide out x minus 1 by doing my synthetic division. I've got my 1, and then my coefficients inside, 2, 0, negative 5, and 3. I bring my 2 down. 2 times 1 is 2. 0 plus 2 is 2. 2 times 1 is 2. Negative 5 plus 2 is negative 3. Negative 3 times 1 is negative 3. And 3 plus negative 3 is 0. Okay, we were expecting the 0 because we knew that x equals 1 is a 0 of p. But that tells us that we can factor our polynomial as x minus 1, since 1 is a 0. And then these here are the new coefficients. 2x squared plus 2x minus 3. Well, now we want to continue to find the zeros, so we are setting this equal to 0. Now, we've got this quadratic that needs to equal 0. We can either factor it or use the quadratic formula. Let's go ahead and try to factor it first. We should always want to factor first. We should get fluent enough with factoring that it seems easier than using the quadratic formula. Okay, so you try and factor this out, and this is going to be, let's see, we need a 3 and a 1. So let's do a plus, oh, I'm not sure that we're going to be able to do it. Let's see, minus a 1 and plus a 3. That's going to give us a plus x. That's not going to give us a plus 2x. So if we were to flip it around, well, we'd need to add 3 and then minus 1. And that's not going to work either because that's going to give us a 6x, a minus x. That's going to be a plus of 5x. So it looks like it doesn't factor. All right, so now that we're sure that we're not going to factor, let's go ahead and use the quadratic formula. We have x equals negative b plus or minus the square root of b squared minus 4ac over 2a. So we've got negative 2 plus or minus the square root. This is 4 plus 24, which is 28 over 4. Okay. All right, now, well, this is 28 is 4 times 7. So we can take the square root of 4 and get a 2. All right? And then just cancel a common factor of 2. So we get negative 1 plus or minus root 7 all over 2. And those are the real zeros, the other real zeros of p. Okay, let's go ahead and do it again. Here we're told that x equals 1/2 is a 0 of multiplicity 2. And then we want to find the real zeros of p. So again, we can use synthetic division to factor out the x minus 1/2. We have our 1/2 on the outside, and on the inside of our bracket we have our coefficients. 4, negative 4, negative 11, 12, negative 3. We bring our 4 down. 4 times 1/2 is 2. Negative 4 plus 2 is negative 2. Negative 2 times 1/2 is negative 1. Negative 12 plus, negative 11 plus negative 1 is negative 12. Negative 12 times 1/2 is negative 6. 12 plus negative 6 is 6. And 6 times 1/2 is 3. And now negative 3 plus 3 gives us 0. Okay, now we've just factored out essentially an x minus 1/2. But it's a 0 of multiplicity 2. That means that x minus 1/2 shows up twice in the factored form. That means we can do it again. Put 1/2 out here. And now we're just using the coefficients of what we're left over with. We don't need to worry about the 0 because that's the remainder. So we bring the 4 down. 4 times 1/2 is 2. Negative 2 plus 2 is 0. 0 times 1/2 is 0. Negative 1/2 plus 0 is negative 12. And negative 12 plus times 1/2 is negative 6. And now 6 plus negative 6 is 0. And again, we were expecting this 0 because we knew that 1/2 was a 0 of multiplicity 2. So it had to work twice. Now, what we've arrived at is the x minus 1/2 is a factor twice, and these are the coefficients of what's left. Now, we've done this twice, which means our degree drops by 2. So now we've got x squared. So we've got 4x squared plus 0x and then minus 12. Okay, we are finding the zeros. So we're setting this equal to 0. Well, now this is pretty easy to get because we're setting that equal to 0. We can add 12 to both sides, divide by 4, and then take the square root. So x equals plus or minus the square root of 3. Let's do it again. We've got this polynomial. We're told that x equals 1 is a 0. So let's go ahead and divide out the x minus 1 factor that we know. We have our coefficients of 1, -6, 11, and -6. We'll bring the 1 down. 1 times 1 is 1. -6 plus 1 is -5. -5 times 1 is -5. 11 plus -5 is 6. 6 times 1 is 6. And -6 plus 6 is 0. So I now have a factored form of x minus this number, minus 1. And these are the coefficients of what's left. So I've got x squared minus 5x plus 6. Now I'm trying to find my zeros. And this quadratic definitely factors nicely. That is a nice clean x minus 2 and x minus 3. So my zeros, well, I have my x equals 1, but I also have x equals 2 and x equals 3 for the zeros of this polynomial. Okay, that's a lot of practice with those. Why don't you go ahead and try the same thing. You're told that x equals 8 is a 0 of this polynomial. Let's go ahead and find, well, we need to find the smallest 0 of p, but that probably means we're going to have to find all the zeros of p. So go ahead and pause it and see what you can do with it. Okay, we're going to go ahead and set up our synthetic division. We have an 8 on the outside, because that's our 0. And then the coefficients, 1, -24, 192, and -512. The numbers look pretty bad, but it should work out nicely since we're told that 8 is a 0. So we'll bring the 1 down. 1 times 8 is 8. -24 plus 8 is -16. Okay, then we've got 8 times -16, and that is a -128. Okay. 192 plus -128 is a positive 64. And then 64 times 8 ends up being 512. And it better be, because we know these need to cancel and give us a 0, since 8 is a 0. All right. Well, this tells me that I've got x minus 8, and then these are the coefficients of what's left when I factor it. So x squared minus 16x plus 64. Well, this quadratic, we're finding the zeros. This quadratic factors. In fact, that is x minus 8 times x minus 8. Well, that's crazy. We just found that x equals 8 is actually the only 0. It's a 0 of multiplicity 3. Okay, so the smallest 0 of p is still x equals 8.